Hello everybody, so this is the first video associated with Chapter 4 of the Reinforcement Learning course. So the purpose of this chapter is to study an approach called dynamic programming to solve Markov decision problems or Markov decision processes. Okay, so this chapter covers Chapter 4 from the textbook, so feel free to have a look at the textbook. For if some explanations are not clear in my slides. The textbook is very well written, so feel free to consult it. Okay, so in the previous chapter we introduced Markov decision processes, which involve sequential decision making. So you have a sequence of state, then in a state you perform an action, receive a reward, and then jump into a next state, do another action, receive a reward, next state, etc. Okay, so you have this state, action, reward sequence, and the goal is to optimize the policy, which is the mapping from the various states to your various actions, so as to maximize the expected future discounted reward you would receive. Okay, so in this chapter we also introduced the value function. So first the state value function, and then after the action value function. So in a nutshell, the value function of a given state is the expected discounted reward if you start in that state. So it's what rewards you're expected to receive in the future if you start in that state. So there's the value function associated with a policy, which is expected rewards you will receive, you're expected to receive if you follow that policy. Or there's the optimal state value function, which is the expected discounted rewards you're expected to receive if you follow the optimal policy. Okay, so we've introduced these value functions, and we saw recursive equations they had to satisfy, such as the Bellman equation. But in practice, the value function for a given problem is unknown. So one of the key problems of dynamic programming is to try to compute this value function. So the purpose of this chapter, which is to introduce dynamic programming algorithms, will provide approaches to compute or at least approximate the value function associated with a Markov decision process. Okay, so the purpose of this chapter is to apply or at least calculate the value function in practice, which is unknown. So we know it exists from the previous chapter. We defined it, but now we're going to show how to compute it in practice. Okay, one key element I want to highlight here is that dynamic programming requires a perfect knowledge of the environment. And what do we mean by environment? We mean transition probabilities between states. Okay, so if you are in the states and you do an action, dynamic programming assumes that you know exactly the probabilities of landing in each possible subsequent state. Okay, so in practice, sometimes this is unrealistic, but for some problems, whereas for some other problems, this indeed applies. Okay, so for some other problems, you do know the environment. Okay, so as just mentioned, sometimes classical dynamic. So DP here stands for dynamic programming. Classical dynamic programming algorithms are sometimes of limited utility in reinforcement learning, because of that assumption we told. So in practice, there are many problems where you don't know how the environment behaves. So you can interact with the environment, but you don't have the probability distributions of landing in the various states in practice. So this is one reason why reinforcement learning will be useful in subsequent chapters. And furthermore, we're going to see that the dynamic programming algorithms sometimes they entail unrealistic computational expenses for some problems. Okay, so we're gonna see that sometimes the algorithms proposed here for problems that are very very large, they become impossible to apply because it would take way too much time to compute things. Okay, so does it mean for these problems? Well, does it mean dynamic programming is not useful? The answer is no. So first, there are other problems where they are well applicable. So when transition probabilities are known and the number of, at least the dimension of the problem is not too large, dynamic programming can be applied. And nevertheless, the reason why we study that is dynamic programming provides a theoretical foundation for all reinforcement learning algorithms we're gonna study subsequently. Okay, so understanding reinforcement learning requires first understanding dynamic programming. Okay, so it's kind of a building. Dynamic programming is a building block, foundational block in the theory of reinforcement learning. So it's very important to understand it. Okay, so let's say we have some Markov decision problem and we have a fixed policy pi. Okay, so recall the policy pi takes as an input a state and an action and returns a number between 0 and 1, which is the probability of taking an action in a given state. So the first problem we're going to consider here is to compute v pi, which is the value function, state value function associated with that policy pi. And the action of trying to calculate this state value function for a fixed policy pi is called policy evaluation. Okay, so policy evaluation entails calculating v pi for some pi. Okay, so just a quick recall from chapter 3. V pi had to satisfy this relationship. This relationship was called the Bellman equation associated with a fixed policy pi. Okay, so this is the Bellman equation, and we mentioned in the previous chapter that this is some form of recursive equation that had to be satisfied by v pi. Okay, so for a given state S, v pi of S could be expressed as some summation of some probability terms times the reward plus gamma times the value function v pi also. Okay, so v pi can be expressed as a sum, weighted sum of v pi's in other successive states or successor states. Okay, so do we know how to solve these equations in practice? Well, assuming that so if we fix pi, this term is known, and here in this chapter we're gonna assume that we do know the function p here, which is the transition density function or transition probability function. Okay, so if we know this and this, calculating v pi here becomes simply solving a system of linear equations. How many equations are there? There's here, this is cardinality of stylized S. Stylized S is the set of all states, and cardinality of S is just the number of states. Okay, so the number of equations here to be solved is cardinality of S, where you have one equation per state. Okay, so in theory, well, we know how to do that. You could use linear algebra to do that, but in practice, it's sometimes too cumbersome to do that. Okay, why is that the case? Well, if there's 10 to the power 20 states, solving a system of equations of that many equations is often impractical in practice. Okay, you cannot do that. There are too many equations. Numerically, it's just not feasible. Okay, so this approach of calculating v pi through solving a system of linear equations, it can work well if there are not many states, but if the number of states is too large, then it becomes impossible. So here what we are going to do, we're going to propose an iterative approach which produces a sequence of functions vk, okay, so v0, v1, v2, etc., and that these function v's, they will converge to the value function. Okay, so instead of directly calculating v pi, we're going to show how to come up with an iterative procedure to obtain a sequence of functions, and these functions will converge to v pi. Okay, so this is very nice because if we go sufficiently far in that sequence, we're going to have a very good approximation of the value function. So the procedure we're going to discuss next is known as iterative policy evaluation. Okay, so we don't exactly calculate v pi as in the what we call regular policy evaluation, but we obtain an iterative approximation of it. So this is called iterative policy evaluation. So how does it proceed? Well, first, so we're going to discuss how to come up with that sequence. Okay, so the first thing we do is to select the first function in that sequence, v0. So v0 will be chosen arbitrarily. Okay, so for all the states s, we can set initially v0 of s is equal to any possible number you want, any real number. One exception to that is that in terminal states, if any, so for episodic tasks, if there's a terminal state, the value at that state must be given 0. Okay, so for all terminal states where the episode ends, you put 0 as the initial estimate of the value function, which is not only an estimate, it's the exact true value in these states. But for all non-terminal states, you can put any number you want as initial estimates of the value of these states. And then what we're going to do, we're going to define recursively vk's, in fact, vk plus 1 in terms of vk. Okay, so assuming we know or we have an estimate vk of the value function, this recursion we show in this slide tells us how to obtain the next function in the sequence, which is vk plus 1. Okay, so here, let's recall something. Okay, from the previous chapter, we had a relationship which was of the form. So v pi of s was the expected value under policy pi of rt plus 1 plus gamma v pi of st plus 1 given st is equal to s. Okay, so this was the Bellman equation for policy v pi. We could express the value function in the states as the expectation of the reward plus the discount factor times the value function at the successor state. Okay, so here what we're going to do in the rule below, we're going to replace v pi, which is unknown, by the current estimate of it. So we replace v pi by vk. And then we're going to calculate this expectation, and this will give us the next estimate, vk plus 1s. Okay, so basically what we do, we take the Bellman equation, but here on the left side, this is the next estimate, and on the right side, this is the previous estimate. Okay, so this is how we perform the procedure, which is called iterative policy evaluation. Okay, and this expectation here, what are the unknowns? It's the reward and the next state, or the successor state. So here, how do you express this expectation? Well, when you're in state S, first you select an action, so you have to sum over all actions and take their respective probabilities given you're in state S. And then once you take an action, you end up with a random successor state and a random reward. So you have to consider all possible successor state, all possible rewards, times of the probability of these next state and reward happening given your current state and action, and times this. So this is the next reward, r, plus gamma times the value function. But here, as we said, it's not the true value function, it's our current estimate vk. Okay, so this rule is the iterative policy evaluation, where you obtain a new estimate of the value function vk plus 1 in terms of the value function vk. Okay, and this, you have to do that for all s. Okay, so for all states you can apply this formula. So this gives you a new estimate vk plus 1 of the state s for all possible s. Okay, that's great. So we give the kind of intuitive rationale of why we're doing this. We use the Bellman equation, but since we don't know the exact value function, we can replace it with our current estimate to refine our estimate. Okay, so this is a slight intuition about what we're doing, but does it make sense? Is it valid to do that in practice? So this, we'll answer that question shortly. Okay. So one quick note about this is that the function vpi is clearly a fixed point of this update rule. Okay, so here I'm not going to assume that students have an extensive understanding of the fixed point theory. So if you were exposed to that in your analysis course, for example, that's great. But otherwise, don't worry about it. Okay, we'll explain this. Moreover, I've put supplemental material in chapter 4. So if you're interested to know a bit about fixed point theory and what we call the Banach contraction theorem, you can refer to these slides if you want to learn more. Okay, so these slides are not mandatory, the supplemental material, but if you're hungry for learning more, it's a good idea to have a look at them. So what do we mean by vpi is a fixed point of the previous update rule? It means that if we had a perfect estimate of the value function, so if at some point at some iteration k, we managed to have a perfect estimate of the value function. So if vks was equal to v pi s for all s, then applying the policy iteration would lead our estimate unchanged. Okay, so if vk of s is v pi of s, then vk plus 1 of s would be also equal to v pi of s. Okay, so if we have a perfect estimate of the value function, then this estimate would be invariant to an application of the iterative policy evaluation procedure. Okay, why is that the case? It's from the Bellman equation. So if we go back here, so if we have this, and if we plug the true value function v pi here, then this right term has to be equal to v pi s here. And this is simply the Bellman equation. So this is why v pi would be a fixed point, meaning that if we plug v pi here, we would obtain also v pi here. Okay, this iteration here would leave the function v pi unchanged. Okay. Furthermore, the sequence vk, so the sequence of functions vk, can be shown under very mild conditions to converge to the true value function v pi, regardless of v0. Okay, so for any starting point v0, any initial estimate of the value function, then your sequence of estimate will converge to VPy under mild condition. Okay, so in the class I won't discuss these mild conditions, but again, if you go to supplementary material, you have a more extensive discussion of this. So in a nutshell, the requirement for this is that the Bellman operator, again, this is only if you want to know more. Okay, but if you want to know more, in the slides we define what we call a Bellman operator, and if this Bellman operator is a contraction mapping, then the fixed point theory entails that you have a unique fixed point and that your sequence VK would converge to that fixed point. Okay, so this is what I just said. This is not mandatory to know, but I encourage you to learn about it if you're interested. Okay, so what we have to know is that for most cases of interest, VK will converge to the true value function. Okay, so well, let's go back here. Here we show how to compute VK plus 1s in terms of VK for all states S prime, and the action of computing VK plus 1s for all states S, this is called how we call a sweep through the state space. Okay, so a sweep through the state space. The state space is S, so it means that we go through each single state S to update its value. Okay, so let's say there are 3 states, 1, 2, and 3, or let's call them A, B, C. Then you start with state A, you apply this for state A, you get a new estimate of the value of state A. Then you do that for state B, new estimate for state B. Then you plug S is equal to C here, get a new estimate for state C, and this is, you have been sweeping through all the states to get new values for their estimated value. Okay, so one point worth mentioning is that we showed, well, or we stated, which can be proven, that VK will converge to the true value function at k goes to infinity. However, this might only be in the limit. Okay, so for example, if how to say that? So unless you have you're very lucky and you have like some kind of weird luck where you have a proper estimate of the value function initially, VK will converge to VPy, but might never be exactly equal to VPy. Okay, so when you apply this iterative policy evaluation, in practice, you need to stop it after a finite number of iterations. Okay, so you can calculate V1, V2, V3, V4. Maybe after V100, it's enough and you have to stop there because you don't have an infinite number of time to compute your things. Okay, so in practice, how do we apply this? Well, we would stop at some point, but when do we decide how to stop? A common stopping criterion entails stopping when your the difference between your previous estimate and your next estimate is smaller than some tolerance parameter called theta for all states. Okay, so when the maximum across all states of the variation of your estimate of the value function is smaller than theta for some suitably chosen theta, then people will stop the algorithm. Okay, so theta here, it's often called a tolerance parameter. Okay, so that's nice. This allowed us to calculate the value, or at least have an approximate value of the value function for a given policy. Okay, so in practice this is nice, but we're not over yet, because it's good to be able to calculate the value of some given policy, but in practice we often want to do more than that. Okay, so in practice, we don't want to know for a fixed policy, but we want to know how to improve our policy so as to eventually try to converge to the optimal policy. Okay, so the purpose of these dynamic program or Markov decision processes is to try to find the best possible policy. So we're going to see how computing the value function for a given policy can help us achieving that goal. Okay, so we're going to see that sometimes we might want the value of some policy in itself, but moreover, we can use that estimate because it will point out towards how to improve our policy. Okay, so for the upcoming discussion, we will only consider what we call deterministic policies. Okay, so what we mean by deterministic policies, it's policies where the probability of taking the various respective actions in a given state is either 0 or 1. Meaning that we consider only policies where if you fall in a state S, then you know exactly with probability 1 what action you will take in that state S. Okay, so there's no randomness with respect to which action you would select in this state. Is this a problem? Well, no, because it can be shown that in the dynamic programming context, the set of optimal policies always contains at least one policy that is deterministic. Okay, so we said sometimes there are many possible optimal policies, but we can show that there always exists at least one optimal policy which is deterministic. Okay, so we will stick with that with these deterministic policies for the sake of the discussion. Okay, so as we mentioned in deterministic policies, when you enter a state S, we know exactly which single action we're going to take in that state S, so we can denote that action by pi S. Okay, so it's a bit an abuse of notation because pi was a density function or a probability mass function previously, but we're going to use this abuse of notation regardless to make things simple. So pi S determines the action A taken, if we fall in state S according to the policy. Okay, so let's say we have a policy which tells us, like in each of the states, which actions we should make. What we're interested to do is to improve on our policy. So determine, is there a way to get a better policy which would lead us to higher value? Okay, so how can we do that? Well, we're going to see next that this can be done through what we call what we called previously the action value function. Okay, so the idea we're going to see is that if we follow some policy, then the action value function tells us what is the respective value of each action in that state. And the value of an action is the expected reward you will receive if you take action A right now, and then subsequently for all subsequent steps you follow policy pi. Okay, so the idea is if we have that action value function, it would be relevant to determine if your action with the highest possible value is the one that your policy uses. Okay, so if there's an action which has a higher value than what your policy pi action would give you, then you should rather switch to that new action when it's state S. Okay, so this is the idea we're going to pursue. Okay, so a quick recall, the action value function also satisfies its own Bellman equation, which was of the following form. So here, let's recall that the action value function in state S, if you select action A in that state, is the sum across all possible subsequent state and all possible rewards of the probability of obtaining these subsequent states and rewards times the reward, okay, plus gamma times the state value function in the successor state. Why the state value function here? It's because we said that starting from the successor state, we're gonna the assumption is we're gonna follow policy pi. Okay, so we can value the rest of rewards as the value following policy pi. Okay. So as we discussed briefly in the previous slide, we're going to see that if we're in the state S and there exists an action A which is different than pi S, so which is different than the action provided by our policy. So if there exists such A which has a higher value than pi S, meaning that q pi SA is greater or equal to q pi S pi of S, then it would be preferable to follow a new policy, which we are going to call pi prime, which does select this new action. So it might be better to follow policy pi prime, where pi prime of S is that new action A which has a higher value than pi S. Okay? Because what the action value says is that let's say we have A having a higher value than pi S. It means that it's a better idea for the next play or the next transition at least to select action A in that state S instead of pi S. Well, if it's better to do that right now in the next time step, well, it might be better to do it the rest of the time. Okay, so if it's optimal right now to select a state A in that state S and better than selecting action pi S, if it's better right now, if we face that state again S in the future, it should be better also in the future to select this action A rather than pi S. Okay, so this is the intuitive idea with respect to what we're going to do. Okay, so we're going to prove that and put that into formal theorems. Okay, so this result or this idea is expressed formally through theorems and results of the next slide, and this result is generally referred to the policy improvement theorem. Okay. So let's state what the policy improvement theorem is. Okay, so let's assume that we have two deterministic policies, pi and pi prime. And we're going to assume that for all states S, the value of the action pi prime of S in state S is greater or equal to v prime prime S. Okay, so let's recall this guy is equal to q pi S pi of S. Okay, so it's the value function if you select action pi S in state S. This guy here. Okay, so suppose we have a new policy pi prime which provides a higher value for its actions in each respective state S than the current policy pi. Then it can be shown that the policy pi prime must be as good as or better than pi, which is that for all states, the state value function v pi prime is greater or equal to the state value function v pi. So this clearly shows that pi prime is a better policy than pi. Okay, so this gives us an inequality that is not strict. Okay, so it's greater or equal, but it doesn't say greater. However, if we had impose an additional condition, so if there exists a state S1 such that the value, action value of action pi prime S1 in state 1 is strictly greater than the value of state 1 according to policy pi, then v pi prime s1 is strictly greater than v pi s1, meaning that the policy pi prime is strictly better than the other policy, at least in state s1. Okay. So let's prove, or at least it's not a formal proof, but I'd say it's a sketch of proof for the previous result. Okay, so let's go back one slide. Let's assume that our first assumption here, that q pi s pi prime s, so the value of action pi prime s in state s is greater or equal to the value of state s according to pi, and this for all states. Then, okay, so this is our assumption, the first line. This is our assumption from the first theorem. And then let's recall what is q pi s pi prime of s. Okay, so here, by definition, or well, it's not the definition, but we've shown previously that q pi s pi prime s is the expected reward at the next time step plus the discounted value function in the successive state. So here, that value function is v pi because we said that when we consider q pi, all subsequent actions are selected based on policy pi. So for that reason, here we have v pi and not v pi prime. Okay, but this given the current state is s, okay, as we assume here, but the current action we take is pi prime of s because we assess the value of action pi prime s taken right now at the current step. Okay, so this here, we can express it as the expectation under policy pi prime of rt plus 1 plus gamma v pi st plus 1. Okay, because here the next reward and next state are determined according to this action, which stems from policy pi prime. Okay, but now we can still use that relationship here, but instead of using s, we're going to use capital st plus 1. Okay, so this relationship holds for all s. So for that reason, we can apply it for s is equal to capital S plus 1. So this guy here becomes smaller or equal to this guy here. This is how we go from that line to that line. We apply this relationship, which was our assumption in the theorem, but now we apply it to state st plus 1. Okay, and now again, we've seen in previous chapter, well, this is exactly the same rationale we've used here. Okay, so here, this equality here, we applied it for s, but we can also apply it for state st plus 1. Okay, so q pi st plus 1 and this action pi prime st plus 1, it is the expectation under the policy pi prime of the next reward plus gamma times v pi st plus 2. Okay, so here, why is it v pi and not pi prime? It's because when we calculate q pi again, we assume that for all states subsequent then to st plus 1, we're going to follow policy pi. Okay, so this is why there's a pi here for successor states, but here we have pi prime because the next the action right now taken at time st plus 1, here it's assumed to be pi prime of st plus 1. So this is why the pi prime is found in this expectation here. Okay, and here when we calculate q pi, this is given the current state and the given the current action being selected according to policy pi prime. Okay, and here we can use the nested expectation theorem. So recall that we had a statement which said that expectation of x given g2 given g1 is equal to expectation of x given g1 if g1. So I'm gonna write included in g2. So what here, this inclusion, and if you do some advanced math, it has a formal meaning here, but here informally it's just that g1 contains less information than g2. Okay, so here if we look at that, g1 would be that current information of st, and the next state here, okay, so we could have that, but we could also condition on st, but here this condition on st, it would disappear because of the Markov property. Okay, so if we know st plus 1, all which will happen after st plus 1 is not impacted by st, it's only impacted by st plus 1. Okay, so this is why this st has disappeared in here, but we can still place it here, and then from this we would obtain two nested conditional expectation, which could be expressed simply as one single conditional expectation given the coarser information, which is given the state S. Okay, so from that, this is why the expectation operator just disappears here. It's this double expectation theorem that we apply. So here, once we do that, we end up with this relationship. And then, okay, so we extended, this is RT plus 1 plus gamma VT and ST plus 1. We can do that another iteration. So it's RT plus 1 plus gamma RT plus 2 plus gamma squared V pi. But we could continue on. So we could obtain, if we do the again and again and again the previous steps, we could get something according to the following. So it would become expectation under policy pi of the next reward plus gamma, the reward times the reward in 2 steps, plus gamma squared, the reward in 3 steps, etc. until infinity. And here, to have that, what we assume here is that this term will converge to 0. Okay, so the gamma to the power something times v, or let's call it gamma to the power n times v pi st plus n, we assume that this will converge to 0 as n goes to infinity. Okay, so that we will discuss in the next slide. Okay, but if we apply these steps, provided this last term converges to 0, then we have the following geometric sequence of rewards. Well, it's not exactly a geometric series, but sorry, it's like the first reward is discounted by gamma to the power 0, second reward by gamma to the power 1, third reward to the power gamma 2, etc. And here, this expression, it's the sum of expected discounted rewards if you follow policy pi, which is simply v pi of s. And this completes the proof. This shows that for all states S, v pi of s is smaller or equal to v pi prime of s. So we've shown that pi prime is indeed either equal or strictly better than policy pi for all states. Okay, so whoops. Okay, so in the statement of the last theorem, there was also a part with a strict inequality. We won't give a proof for that, but the steps are pretty similar to what we did. Okay, so you can use similar ideas to prove the second part of the theorem. And in the previous theorem, as we mentioned, let's go back one slide, we assumed that this term would converge to 0 as let's say this number 2 here and this number 2 here, eventually they would become k, and if k tends to infinity, we hope that this term goes to 0. Okay, so we relied on the fact, or on the assumption that the expectation under policy pi prime of gamma k v pi of the state st plus k given the current state vanishes. So vanishes means converges to 0 when k goes to infinity. So this, can we prove that? Well, in the case where gamma is strictly smaller than 1, this is obvious. Why is that the case? It's because if gamma is smaller than 1, this first term here, gamma to the power k, will converge to 0, and the second term here is bounded. Okay, so the value function, it's the sum of expected discounted rewards in the future, but the future rewards are bounded by the maximal possible rewards. Okay, so if we have a finite MDP, okay, I haven't put finite MDP here, but in what follows, we're gonna assume that our Markov decision process is finite. If this is the case, then v pi of s, which is the sum of discounted rewards, is bounded by the sum of discount factors to the power j times the maximum reward. Okay, so the sum of future discounted rewards is bounded by the sum of future maximum rewards, which is, this is a geometric series, which is maximum of the reward divided by 1 minus gamma. And gamma is smaller than 1, so this is different than 0. Okay, so for this reason, if we have a discount factor smaller than 1 and a finite MDP, then this term converges to 0 as k goes to infinity, and this is bounded by some value, so the product will converge to 0, and what we did is just fine. Conversely, in other cases, if you have a undiscounted task that is episodic, which means that we have a discount factor gamma is equal to 1, but there's an absorbing state or a terminal state S prime to which you're certain to end up eventually, then it means that in the limit, the probability to not be in this absorbing state becomes 0. Okay, so we said that for episodic tasks, you're certain to reach that terminal state at some point, so the probability to not be in this state must converge to 0. Okay, so in that case, if we go back to this term, so here this term, when gamma is equal to 1, this first part disappears, so we're stuck with only this part. But here, this part here, if we have a finite MDP, okay, it becomes smaller or equal to the maximum value, the maximum of the value function across all the states. Okay, so here again, if we want a bound for this, we could assume that all rewards are equal to their maximum, and then this would get us a bound for the value function, and even like, well, in fact, it would be an upper bound to this quantity. So maximum of this times the probability that the state st plus k is different than the absorbing state. Okay, so because here, when we reach the absorbing state at time t plus k, the value of that state becomes exactly 0. Okay, so here this expectation is equal to the sum of the value functions in all possible states times their probability of getting to these respective states. But for all absorbing states, the value is 0. So this expectation must be simply equal to the sum of the value of non-absorbing states times the probability to reach these absorbing states. And here, these value of these non-absorbing states, they're bounded by the maximum possible value function here. Okay, so this is a constant, and this here converges to 0, so the product must converge to 0. Okay, so the previous statements we relied on, which is, let's go back here, that this term converges to 0, then this is satisfied in practice. Okay, both for either if gamma is smaller than 1 or if you have an episodic task. Then you might ask, well, what if gamma is equal to 1 and then you have a continuing task? Okay, so you don't have absorbing states, or you might not reach these states. Well, the answer is, in these cases, the value function itself might not exist. Okay, because if you summed undiscounted rewards over an infinite number of times, that expectation might be infinite. Okay, so this proof would not work for undiscounted continuing tasks, but the value function wouldn't even be defined probably in these cases. Well, for many of these cases, maybe not all. Okay. So this okay, we saw the policy improvement theorem, which tells us that if we have some policy pi and we can calculate its value function v pi, then we can check the action value function associated with this v pi. Okay, so we can check the q pi associated with this v pi, and then this q pi indicates us how to improve on our policy. Okay, so for any state S, we can check the value of each possible actions according to q pi, and if there are other actions that are more promising than the one currently used in our current policy, then we can design a new policy simply using these more promising actions. And this, according to the policy improvement theorem, gives us a better policy which has a value function that is greater or equal to the value function of our original policy. Okay, so this is words, but now we can explain in equations how we do that. Okay, so if we have a policy pi, then we can compute v pi and q pi associated with this policy. So in practice, as we said, we might not be able to compute it exactly, but we can have a very good approximation of it. And once we have this approximation, then we can calculate for all states S, we can determine what is the action. Okay, let's forget about this term here, but we can check q pi SA for all values of A, and then for check the value of A across possible actions in that state S, which maximizes the value of the action. So we take the best possible action in that state, and this best possible action, according to the function q pi, we will define it as pi prime of S. So we can define a new policy for which the action selected in state S is simply the one which maximizes the value of that action according to our policy pi. Okay, and here this q pi SA, as we've seen previously, it's possible to express it according to the following equation. So q pi SA, it's simply the sum across all possible successor states and rewards for the next time step of the transition function times the next reward plus gamma times the value function at the next state S prime. Okay, and if we do that, it's guaranteed by the policy improvement theorem that our next policy will be at least equal, but maybe better than our current policy because it has a highest value function for all states S. Okay, so applying this procedure where we have a current policy, and then for all states we check the most promising actions and design a new policy using these most promising actions, this is known as policy improvement. Okay, so it's a very important term in dynamic programming. Okay, one quick note here. So let's say we check our function q pi sa, and we find that there's more than one action A which maximizes this value. Okay, so there might be two actions, A1 and A2, which both maximize the value of the action. So in that case, how would we select one? Well, the answer is it doesn't matter. Okay, so we could address ties where two actions are equally valuable by arbitrarily picking one of both, since these actions point out to the same value. Okay, so if you might have cases where two actions yield the same value. Well, in this case, you can pick any one of them and it shouldn't be a problem. Okay. So now it's good. So we can take some policy pi, and then we know by applying our policy improvement how to get a new pi prime to which improves on the previous policy. Okay, so now once we do that, well, you can get pi prime, but maybe you can apply this and start with pi prime and still get another better policy, pi prime prime. And then repeat that, get another better policy, pi prime prime prime. And continue like this until you get a very good policy. But then the answer is, when do you stop? So if you do that, will you uncover eventually the optimal policy? That's a very relevant question. Okay? So, let's study what happens. Okay, let's assume for now that, let's say we have a policy pi, we try to improve it and obtain a new policy pi prime, but let's assume that pi prime ends up being exactly identical to pi. So policy improvement did not improve on our policy. What does it mean? It means that for all states S, the action maximizing the value of that state S, according to policy pi, is pi S itself, which is the action proposed by the current policy. So it means that when we look at the action value for all, so let's say we fix S, and for that S we look at the action value for all actions, and the best one ends up being pi S, which is our action proposed by our initial policy. Thus, what would that mean? It would mean that v pi S, the value according to policy pi of that state, would be equal to, okay, so q pi S by S, this is simply it's direct from the definition of v pi. So here the value of the action pi S in state S is clearly v pi S, because v pi assumes that we follow policy pi all the time, so the next action will simply be pi of S, of course. Okay, but here from that result here, from our assumption that the policy remains unchanged, it means that the action pi S does indeed maximize the value function for all states S across all actions. So if we replace here q pi SA by its definition, or sorry, not its definition, but through a formula we had in the previous state, this was equal to this guy, expectation of R plus gamma V pi, V pi S prime given the current state is S. This should be ST plus 1. Okay, and this can be expressed as this. Okay, so you sum across all possible next rewards, and next state and next reward of the transition probabilities, which is the probability associated with these next rewards and state of the reward plus the gamma times the next value function, and the value functions are in the next state. Okay, so why is it v pi here? It's because we calculate under policy pi. So if that's the case, well, this being equal to this, it's exactly the Bellman equation. Okay, so if you go back to chapter 3, this is the Bellman equation. Let's change color here. So here, this equality here, this being equal to this. This is the Bellman equation, not for an arbitrary policy pi, but it's the Bellman equation for the optimal policy pi. So it means that pi is an optimal policy. This is very interesting. It means that if the policy is unchanged by our policy improvement theorem, meaning that once we apply policy improvement to pi, we obtain a new policy pi prime which is exactly equal to the original one, then this implies that pi is an optimal policy. Okay, so v pi is equal to the optimal value function itself. So this is very nice because it points towards the fact that you can start with some policy, let's say pi, and then apply policy improvement to get pi prime, apply policy improvement to get pi prime prime, and continue until the policy you have is left unchanged by the policy improvement. And then at that point, when the policy improvement is left unchanged, it means that you've converged to the optimal policy. Extraordinary. This allows us to determine the optimal policy in practice. This is a very, very, very useful and important result. Okay, so in summary, when you have a policy pi, if you apply policy improvement, you will always get a policy pi prime that is strictly better than your original policy pi, because when it's not strictly better, it means that your policy pi will remain unchanged, and it means that the optimal policy is obtained. Okay, so you start with an arbitrary policy pi, then if you apply this, you will always get better and better policies until you reach the optimal one. Okay, now I've went a bit quickly, so I said if the policy is unchanged. However, sometimes if there are many possible optimal policies, you could have the following. So you could have you could alternate, for example, between optimal policies. Okay, so what we mean by the policy becomes unchanged, well, it means that and how can I say that? It means that the value function of the policy doesn't change anymore. Okay, so when I say eventually the policy might not change, well, if there are more than one optimal policies, when applying policy improvement, you can have another policy through that process. Because recall we said that when there are equally valuable actions, we break tie arbitrarily. So eventually you can end up with a new policy that is different but has the same value. So yields exactly the same value function. So in that case, the algorithm still converged in the sense that you still discovered the optimal policy even though the policy is continuing changing. Okay, so let's say you have policy pi 1 and pi 2 which are both optimal, then you could apply policy improvement and get, for example, from pi 1 you go to pi 2 and pi 2 you go to pi 1, depending on how you break ties according to your programming algorithm. Okay, but in that case, you still have identified the value function. Okay, so we are going to stop there for this video. So I'll see you next time for the second part of this chapter 4. Have a nice day.